In the previous lesson, we talked about 3 different methods to find a solution for a system with 2 variables: graphing, substitution, and elimination. Now we're going to demonstrate each of these 3 methods on some problems. Now, because we are using the 3 different methods on the exact same problem, we should get the same answer 3 times. If we don't, then we did something wrong, and we need to go back and check our work. So in our first problem here, we have 10x plus 5y equals 15, and x plus 2y equals negative 6. We want to start out to solve by graphing. Graphing, you can either make a table of 3 ordered pairs for each line, or you can rewrite these equations as y equals mx plus b, put them in slope-intercept form, and use slope-intercept form. I am going to do slope-intercept form for these first. So I'll take that first equation. We need to get the y term by itself, so we subtract the 10x, and now we divide by 5. 10 divided by 5 will give me 2. 15 divided by 5 will give me 3. So I have a new equation, y equals negative 2x plus 3, but it's just a different form of that standard equation, 10x plus 5y equals 15. And then the second equation, x plus 2y equals negative 6. 2y equals negative x minus 6. We can divide by 2. Negative 1/2 x minus 3. So we have the second one in slope-intercept form as well. And for slope-intercept form, b is where you begin on the y-axis. So for this first equation, I will do this in a maroon color. 3 is where I will begin. And then the slope is how you move. So negative 2 for our slope, that equals negative 2 divided by 1. It also equals 2 divided by negative 1, so I can look at both of those fractions. Rise on top, run on the bottom. So if I look at this first one, it says I go down 2 and to the right 1, and draw a dot, down 2 and to the right 1. And we can fill up the whole graph if we want, or we can just grab our ruler and go ahead and draw that line. So we have the first line, and then the second line, y equals negative 1/2 x minus 3, so we'll go to negative 3. And then negative 1/2, we can look at this as negative 1 over 2 or 1 over negative 2. And that could just be if we take the first fraction here, down 1, right 2. Or if we take the second one, up 1, left 2. And I just like making all my ordered pairs because it helps me line up my ruler a little bit better. And so we line up our ruler and we draw another line. And there we have our 2 equations graphed on this same coordinate axis. And now we have to determine what's the solution. Just like in the previous lesson, the solution is going to be the one ordered pair that solves both, or the one place on the graph where both equations intersect each other, and that ordered pair is 4, negative 5. I can plug this in and make sure that it works, so we can check it. 10 times 4 plus 5 times negative 5. Does that equal 15? And I have 40 minus 25. That does indeed equal 15. And the other equation, 4 plus 2 times negative 5. Does that equal negative 6? 4 minus 10 does indeed equal negative 6. So I have an ordered pair that works. Next up is solving by substitution. I'll copy my system over so that I make sure that I have it. Substitution says you're going to take one equation and solve for one variable. Looking at the two equations here, if I try to solve for a variable in the first equation, I'm going to have to divide by something, either 5 or 10, to get a variable by itself. But if I look in the second equation, I have an x, a single x. So all I would have to do is subtract 2y and get x by itself. So when we're solving by substitution, we get a little bit of freedom here. We get to decide which equation to choose to solve for a variable and which variable we want to solve for. There are 4 different possibilities every single time. Take the first equation, solve for x. Take the first equation, solve for y. Take the second equation, solve for x. Take the second equation, solve for y. And it does not matter what you do. If you're doing everything mathematically correct and using the rules that we've established for solving equations, then you could use any of those and end up with the correct answer. It's kind of nice to choose the variable that's the easiest to solve for, and that way you're lessening your chance of mistakes. So I'm going to choose x in this second equation and solve for x. X plus 2y equals negative 6. We'll subtract 2y from both sides, and we get x equals negative 2y minus 6. Once we solve for x, now we go to the other equation. You take one equation, solve for a variable, and then you use it in the other equation. If you try to plug it in the same equation, you're not going to get anything out of it. It's going to equal itself, and the variables are going to drop out, and you're going to be like, what's going on? So you never use the same equation twice in a row. Use one equation, and then go to the other equation. So we'll go to the 10x plus 5y equals 15. And what I want to do is take this expression for x and substitute it into the other equation for x. So we'll write it out. 10x plus 5y equals 15. X is negative 2y minus 6. Notice when I plug this in, now I have one single equation with only y's in it. That's my goal. I want to have one equation with one variable so that I can solve for that one variable and then go back and solve for the first variable. Multiplying all this out. So now we have an equation with just y's in it. We can combine our y terms, work to get the y's by themselves. A negative 15y equals 75, so we can divide by negative 15, and we get y equals negative 5. Taking that value, now we use y equals negative 5 in either of our original equations. As long as the original equation has x in it, we can use this y to now find x. It does not matter now which equation we use. I like that second equation because it's a little bit simpler, the numbers are smaller, so I'm going to use the second equation. X plus 2y equals negative 6. So x plus 2 times y, which is negative 5. X plus negative 10 equals negative 6, and negative 10 plus 6 will give me 4. These together make up the ordered pair for negative 5, and that is our solution for the system. Notice that's the same solution that we got when we graphed. And we already checked it up top when we plugged it in for the graphing, so we know this is our ordered pair. We got the same ordered pair as we did for graphing, and we've already checked it, so we know that it's a solution. We also know from the graph that there's only one solution because there's only one place where these two lines intersect. Now let's talk about solving using elimination. Just like with substitution, elimination gives us some freedom. The idea with elimination is we want to multiply one or both of the equations by a number or numbers so that one of the variables will get eliminated when we add the equations together. So let's see what I mean by this. if I look here at the way the equations are written, if I try to add 10x plus x, I'll get 11x. And if I try to add 5y plus 2y, I get 7y. I'm not eliminating any variable there. So, equations allow us to multiply by any number that we want to, any non-zero number. I'm going to take this second equation and multiply it by negative 10. So every term gets multiplied by negative 10. Negative 10x minus 20y equals negative 6 times negative 10 is positive 60. And then the top equation, I'm going to keep it as it is. 10x plus 5y equals 15. Now, if I add these equations together, I'm going to add like terms. Now watch what happens. When I add 10x and negative 10x, I get 0. I've eliminated the x variable in this system. 5y minus 20y will give me negative 15y, and then 15 plus 60 will give me 75. Hey, wait a minute. We saw that equation above when we did that substitution. This is a good thing. We divide by negative 15, 75 divided by negative 15 will give us negative 5. Oh, there's our y coordinate that we got above. So again, we're on the right track. And then now, once we do this elimination and we find one variable, it's back to substitution to find that second variable. So we can take the y equals negative 5 and plug it into either of our original equations to find x. Since I plugged it into the second equation before, I'm going to plug it into the first equation this time. But again, it does not matter. Once you find one variable, you can go to either equation to find the other variable. So we'll go 10x plus 5 times y equals 15. 10x minus 25 equals 15, so we can add 25 to both sides. 10x equals 40, so x equals 4, and that gets us that same ordered pair for negative 5. With elimination, I could have, instead of eliminating x, I could have eliminated y. I could have multiplied the first equation by 2 and the second equation by negative 5, and I would have been able to cancel those y's. But multiplying both equations by numbers is a little bit more difficult than multiplying just one equation. So if I can multiply just one equation, I'm going to choose that method. But in both substitution and elimination, there's freedom. There's a little bit of freedom to choose which way you approach the problem and what to do. And last up, there's a little sentence at the bottom. The system is blank and the equations are blank. This is talking about some technical terms that we haven't yet to define. But if I have a solution for a system, we say the system is consistent. So the word consistent means the system has at least one solution. The equations are independent, and equations being independent mean the equations graph different lines. So the opposites of these terms, inconsistent, would mean that the system does not have a solution. And dependent means the equations will graph the same line. So backing up a little bit to what we talked about on our previous lesson, in this first example, which is very similar to the example that we just finished, this first graph, we have a consistent system and independent equations. In this system, we have independent equations because they graph two different lines, but we have an inconsistent system. There's no solution. And in the third, for infinitely many solutions, we have a consistent system, but our equations are dependent. They graph the same line. These same vocabulary words will be used when we talk about a system of 3 variables and 3 equations. Next up, we'll do some more examples with these 3 methods of solving.